All right, we are nearing the end of chapter 3 here, and once again, we are looking at applications of derivatives here. We're not going to be learning any new techniques for differentiation. That's going to come in the very next section. But what we're looking at here is what we call linear approximations and a related concept called differentials. And these concepts become very important in engineering and other levels of math, higher levels of math and calculus and things like that. So just to introduce this topic, we're going to start with the concept of a linear approximation, which is actually just a name that's given to something, a different name given to something we've already discussed. A linear approximation is just a tangent line to a differentiable function. But when we call it a linear approximation, that kind of indicates what we're using it for. So let's suppose that we have some differentiable function, y equals f of x, and we want to find the equation of the tangent line to that function at x equals a. We haven't written this exact formula out yet, but we have done this plenty of times. This formula here would give you the tangent line that we're looking for. And really, it's just point slope form of a line where I've isolated the y in that form. So looking at this, we know that the derivative of f at a gives me the slope of that line. And then I multiply that to x minus a, the x coordinate of the point that's going to occur on the curve, the point that we're finding the tangent line at, plus f of a, that's the y value of that point. Okay, so this thing right here always gives you the equation of a tangent line at a specifically. When we have this equation written out like this, we call it a linearization of f at the number a. And we're going to swap that y out for a slightly different notation. We're going to call it capital L of x, standing for linearization. And basically what a linearization is it's taking advantage of the fact that differentiable functions will appear almost linear if you zoom in on a point closely enough. So if we zoomed in on this graph more and more and more, I would see that the blue curve starts to conform more and more to this red tangent line. They start to look more and more similar. And the idea is that the tangent line, which is a much simpler function to work with, linear functions are among the simplest functions to work with, this tangent line serves as a decent approximation to f of x, which may be a very complicated function to work with, or it may even be a function that we don't have an algebraic rule for. We may just have data that makes up this function. We can use the tangent line as an approximation to points on this blue curve, provided that we're using points that are close to a. So values of x that are close to a. As you can see, in general, the further away you move from a, the less we can expect the linearization to be a good approximation for f of x. And that's indicated by the fact that this curve seems to be separating itself from that tangent line. So linearizations serve as a good approximation when we are close to a, but not so good when we get further away from a. And in that sense, we also call it a local approximation. So let me see if we can come up with an application of this. I want to find the linearization of f of x equals the square root of x plus 8 at a equals 1. And I want to use that to approximate 8.9. So the first thing we're going to do is use this formula for the linearization. But for a, we're using 1. So part of this formula requires me to have f prime. I need to figure out what the derivative of that is. So we're talking about f prime of x. What is f prime of x? Well, this is a straightforward function to do. I would use my chain rule, but it just comes out to 1 over 2 root x plus 8. Okay? Now, it's more specifically, I need f prime of a, which is 1. So this means I'm going to end up with f prime of 1 equals 1 over 2 times the square root of 1 plus 8. That's the square root of 9, which is 3, times 2, that's 6, so this becomes 1/6. in the equation, in my linearization, I also need f of 1. So I'm going to plug that into the original function as well, since I'm going to need that. I'm plugging a 1 in here. That's the square root of 1 plus 8, which is, of course, 3. So now I have all the information that I need. My linearization, L of x, excuse me, is equal to what? It's going to be equal to f of a, which is f of 1, we found that here, 3, plus the derivative, f of a, f of 1, which was 1/6 plus 1/6, times x minus, I said x and I wrote 1. That should be an x right there. X minus a, which is 1. Okay, I can distribute the 1/6 in there if I want to and try and simplify. I'm fine just leaving it as is. Sorry about the sloppiness here. So this is the linearization that we were asked to find. And now it says use it to approximate the square root of 8.9. Obviously, I could plug that into a calculator, but we're assuming that we don't have access to a calculator. How can I approximate this thing using the linear approximation that we just found? Well, before we do that, let's relate the square root of 8.9 back to this function. Notice that the square root of 8.9 is equal to f of 0.9. And the reason I know that is because if I plug in 0.9 right here, then that's 0.9 plus 8, which is 8.9, and then I take a square root. So I'm going to think of the square root of 8.9 as f of 0.9. Now 0.9 is very close to the number 1, right? So because I'm using an x value that's close to the number I used to find my linearization, then the function f of x at 0.9 is going to be approximately equal to my linearization at that same value. And again, that's the point of that linearization. As long as we're using numbers that are close to 1, the equation of this line is a good approximation to the function itself. So I'm going to be plugging 0.9 into this guy right here. 3 plus 1/6 times 0.9 minus 1. And I realized I didn't do this one ahead of time, so I'm going to quickly do that in a calculator. 3 plus 1/6. That's going to be negative 0.1 parentheses there, so that's negative 0.1. Oops, 0.1. It comes out to approximately 2.983. Okay, it's actually 2.983 repeating right there. So this gives me an approximation to the square root of 8.9. Now, does that seem like a reasonable approximation? Well, I think it does, because 8.9 is very close to 9. It's a little bit smaller, though. And I know that the square root of 9 is 3. So I'm expecting the square root of 8.9 to be just a little bit smaller than 3, which is what I'm getting right here. It looks like the linearization is doing its job. Cool. Let's move on. This isn't really a huge section. There's not a ton for us to cover. Next thing I want to do is use a linear approximation at a equals 0 to show that this expression 1 plus x to the negative 1/3 power is approximately 1 minus 3x. So on this side, this is what I would be thinking of as f of x. And what I want to do is show that this would be L of x, the linearization. Notice this expression is linear, so this would represent that linearization, that tangent line. And then it says I want to determine the values of x for which this approximation is accurate within 0.1. So we're going to use this graph for that part, but we'll get there when we get there. First thing I want to do is find my linearization. We saw before that the derivative comes into play there. So what is f prime of x? Well, here again, I'm using my chain rule. This comes out to negative 3 times 1 plus x to the negative 4th power. Okay? And I'm using a equals 0. So what is f of 0? Because that's going to be relevant as well. I'm plugging a 0 in for x here. That would be 1 plus 0 to the negative 3rd, which is just 1. okay? And then I also need f prime of 0, which is -3 times 1 plus 0 to the -4th power. This is equal to -3. So I have all the information I need for my linearization. Again, L of x is equal to f of a, so f of 0, which is 1, plus f prime of 0, which is -3, so plus -3 I can just write as -3, times x minus a. Well, a is equal to 0. This simplifies, of course, to just 1 minus 3x. Notice that's what we got here. So that means that as long as x is chosen close enough to 0, this is an approximation for our original function, which is 1 plus x to the -3rd power. So it's a little bit vague, though, when I say when x is close to 0, because then that brings up the natural question, how close to 0 should x be to ensure that this is a good approximation? And the question is, how accurate do you want your approximation to be? So this is saying, determine the values of x for which the approximation is accurate to within 0.1. Okay? Now what I've done here is I've set up a graph in Desmos, and there's 4 different functions being graphed here. So this red curve right here is the function y equals 1 plus x to the -3rd power. That's the original function that I was trying to approximate in the first place. Now, in order to make sure that I'm getting an approximation that is within 0.1 of the correct answer, what I need to do is figure out for any point on this red curve, what would a value within 0.1 look like. And basically what I'm going to do is just take this function and add 0.1 to it and subtract 0.1 to it, giving me these 2 green curves. Y equals 1 plus x to the -3rd plus 0.1. And this one right here is y equals 1 plus x to the -3rd minus 1. I graphed those, and that minus 0.1. Sorry. That's going to shift the red curve up by 0.1 and down by 0.1, giving me the 2 green curves that you're seeing here. So what that means is that for any value on the sorry, let me back that up. The linearization 1 minus 3x is the blue line that you're seeing here. Okay, so for any point on that blue line that you see, if that point is also trapped between these 2 blue curves, then that would put that point within 0.1 units of the red curve of the function that we're approximating. And this is something you would need a calculator for, a graphing calculator for, because we're not going to talk about a way of doing this analytically. But if you graph all of this in something like Desmos, like I did, you can find where these graphs intersect. And if you notice, the blue line cuts through the bottom green curve up here at this point, and then again at this point. And once it exits that green curve, it's now too far away from the red curve to be within that margin of error that we're looking for. So these 2 points are going to set that boundary that show us how close to 0 our x values need to be to get the desired degree of accuracy in our approximation that we're looking for. So the x values that I'm getting there are the following: -0.1162 and 0.1441. Now notice these 2 values are very close to 0, and that's kind of what we're saying, is that the linear approximation only gives us good approximations when we choose a value of x that's close to whatever we used for our linearization in the first place, 0 in this case. Okay, so a couple of examples on linearizations under our belts. This is going to naturally lead us into the topic of differentials. So what is a differential? Well, we start with some differentiable function f of x, and then from that we're going to derive one of our differentials, or I should say define. So the first thing we do is we define this quantity dx to be one of our differentials. We call this a differential, dx. And right now, we're just going to think of it as a variable. It's an independent variable that can take on any real number, okay? Once we've defined f dx and we have this differentiable function f of x, then we're going to define another differential dy in terms of these two. In particular, we're going to define dy to be equal to f prime of x times dx, okay? And one way of remembering this little formula is, now that we're thinking of dx and dy as quantities in their own right, I can divide both sides by dx and I get this, dy dx equals f prime of x. And notice it just looks like two different notations for a derivative, which of course would be equal to each other since they both represent the same derivative. The key here though is that previously, when we used Leibniz notation to talk about derivatives, dy dx, I told you to not think of these values as quantities in a fraction, because we're not really supposed to treat that like a fraction. But now that we've defined these differentials in this context, we can think of this as a fraction. So what is the actual meaning of these differentials? Well, in general, we think of dx to be a pretty small number, and it's going to represent a change in x. So looking at this image down here, dx is going to be thought of as exactly the same thing as what we've used delta x for in the past. These two, consider them to just be the same thing, okay? Now, here's a graph of my blue curve, which is the graph of f of x. So that's the differentiable function that we mentioned up here. And this red line is the tangent line to that curve at x. So that red line would be given by the linearization of that function at x, okay? Now, as I move from x to x plus delta x, remember delta x is the same thing as dx, the way that we've defined it here, then what does this dy represent? Well, remember, f prime of x represents the slope of this tangent line, right? And so dy dx is that same slope, but represented in terms of rise over run. If my run is dx, then my rise is going to be dy, taking me up to a point on the tangent line. So the way we interpret that is that dy is the corresponding change in my linearization, the corresponding change in my tangent line that corresponds to the change in x, okay? Compare that to delta y, which is not the change in y in our tangent line, but the change in y in our function, the corresponding change in y. So for that, we think of delta y as we've thought of it in the past, f of x plus delta x minus f of x. Okay, it's the change in f, not the change in L, the linearization. However, if dx is small, right, then that means that this point right here, this number on the x-axis, would be relatively close to x, which means the value that we get on our tangent line at that number should approximate the corresponding point on the curve for f of x reasonably well. And so that means if dx is small, the distance between these numbers, if that is a small number, then we're expecting dy to be a decent approximation to delta y. Okay, so that's kind of the key thing here. Let's do a couple of examples where we use this. We may be able to wrap up this section in one video. I'm not sure. So let's suppose we have the function y equals x minus x cubed. We're asked to compute and compare delta y and dy when x is equal to 0 and delta x is equal to negative 0.3. So the first thing we want to find is delta y. Delta y is equal to this, f of x plus delta x minus f of x. So that would be x, which is 0, plus delta x, which is negative 0.3. I'm plugging 0 plus negative 0.3 into this function first. Of course, that's just the same thing as negative 0.3. So I'm going to have negative 0.3 minus negative 0.3 cubed. Probably didn't need parentheses around that first one. Minus f of x. So that's 0 minus 0 cubed, which is just 0. Okay, so there's f of x plus delta x minus f of x. This, if you work that out, is going to come out to negative 0.273. Just use a calculator for that. Okay, how do I find dy? Well, in order to find dy, my differential, remember we define over here dy to equal f prime of x dx. We're given dx in the problem. F prime of x is the derivative of this function. So we can also think of it as y prime, but let's label that f of x right there so that f prime of x is equal to 1 minus 3x squared. Okay, now I need to plug in the value that I'm using for x, which is 0, f prime of 0, which would equal 1 in this case, 1 minus 0. So that means dy, by the way we defined it, is equal to f prime of 0 times dx, which is equal to 1 times, we have dx, which is the same as delta x up here, negative 0.3. That's equal to negative 0.3. Okay, now as we said before, when you choose a small value of delta x or dx, which is what we have here, then delta y and dy should be close. We should think of dy as approximating delta y. And if you notice, these two values are pretty close together, negative 0.3 and negative 0.273. Very, very close together, so the approximation seems pretty good. All right, let's do an actual application of this idea. So one place where this shows up is in manufacturing, where you're producing some kind of a product, and within the production method for that product, there's a margin of error for whatever the measurements of that product are supposed to be. So to give you an example, let's suppose that some company produces these circular discs, okay? And the radius of these circular discs is supposed to be 24 centimeters. But the machinery, the way that it's built, is not perfect, and so there ends up being a maximum possible error in that measurement of 0.2 centimeters. Okay, so that's an error in the radius. We can have up to 0.2 centimeters off of that 24 centimeter radius that we're looking for. And what we want to do is estimate the corresponding maximum error in the area of that disk. Now you can do this without differentials, and it's not terribly hard. The point of differentials, though, is to provide an approximation technique, which is generally a little bit easier than the other method. So how are we going to do this? Well, notice it's saying we want the maximum area maximum error in the calculated area of the disk, and it mentions radius as well. So I want to find some relationship between the area of a disk and its radius. Disk is a circle that includes its interior, so that's a equals pi r squared. Okay. Now a is the function that I'm trying to find a maximum error for, and that error over here, the error would be like the delta y that's appearing here. It'd be called delta a in this case because we're using a different label. And delta a may be difficult to find, but dA, or the dy shown here, but dA in our example, we're trusting that to be a good estimate for delta a. So how do I find dA? Well, according to the way that we define the differential, it's equal to the derivative of a. Notice that a is a function of r, so I'm thinking of this as a function of r that I want to differentiate. The derivative of this with respect to r is just 2 pi r. And then I multiply by the differential. But this time the differential wouldn't be called dx because x is not my independent variable for this function. R is, so I would call it dr. dA equals 2 pi r dr. The dr here represents the deviation or an error in my radius. And we're told that the maximum possible error is 0.2. So that's what I'm going to be setting my dr equal to. Okay, this is equal to 2 pi times the desired radius, which is 24, times the maximum error, which is what dr represents, 0.2. And plugging this in, I get approximately 30.16 square centimeters. This represents the maximum error in the area of this disk, okay? Now, as a final little note before we conclude this section, looking at this, it may seem like a pretty significant error. It may seem like 30 square centimeters is a lot to be off by. So to help put it into context, it's usually more useful to not just look at the raw maximum error as is, but to look at the relative error, which is this value taken relative to what the area of that disk should be. That would be delta A, which is what we're approximating here, divided by the actual area A. And once again, delta A is approximated by dA, so that allows me to use this value right here. Okay, so I want to do that. I want to find that relative error, and then that number will come out to a decimal. If I multiply that decimal by 100, I get the percent error. So it's basically telling me what percent of the area am I off by in this problem. So relative error would be approximated by dA. Say relative error is approximated by dA over A, which is equal to what? Well, dA is equal to 30.16, but what is the area that we're looking at? What we're talking about is an area of the disk that has the correct radius, 24 centimeters. The area of that disk would be pi r squared, so 24 squared. Okay, that goes right into a calculator, and what we end up with here is approximately 0.017. That would be my relative error. Okay, my percent error is what I would get if I multiplied this by 100, just bumping the decimal point over 2 spots, which would be, not that, it would be 1.7%. Okay, so this value, even though it seems pretty large, is only 1.7% off of what we're looking for. Whether or not 1.7% is an acceptable margin of error is up to the manufacturer. So if you get something like this and you think that's too much error, then you can try and fix that as the person who would be in charge of that. Okay, so that's going to be it for section 3.10.